Throughout this section, we've been talking about the idea of local maximums or local minimums and local maximums and how to identify those points. It's also possible for a function to have a local minimum, or in another case, a local maximum, that is also what we refer to as an absolute maximum, or I'm sorry, in this case, an absolute minimum. The difference being that for our function in green, we'll call that n of x, our local minimum and local maximum are not the overall smallest or largest function values that occur, because the function continues increasing to infinity and negative infinity in each direction. But for our function in blue, m of x, we have this local minimum, and whether we follow the graph to the left or to the right, it's headed to positive infinity, meaning this point, this local minimum, is the smallest function value that function will ever take on. So we can also classify that as an absolute minimum. Let's look at how that plays out in a couple of examples and how we would determine that from the function. In example 6, we want to identify any absolute extrema for the function from example 3. In that problem, we ended up determining that we had a local minimum at x equals negative 2/3. The question is, does that function take on any function values smaller than negative 2/3, or is that the smallest overall function value? In order to determine that, we'll consider the end behavior of the function. So we'll take the limit as x approaches both infinity and negative infinity. Keep in mind that to do that, we look at the term with the highest power, meaning to evaluate this limit, we'll just consider the limit as x approaches infinity of 3x squared, meaning we'll be taking 3 times some really large positive value squared, which will give us some really large positive number. Then if we take the limit as x approaches negative infinity of 3x squared, we'll take 3 times some negative number, a really small negative number, but we're squaring that, which will make it positive. So this will still be positive infinity. That is, as x approaches both positive and negative infinity, our function is headed off to positive infinity, but we know we have a single local minimum occurring. That means in this case that that's also an absolute minimum, because the function will never take on a lower function value than it does at negative 2/3. In example 7, we want to look back at our results from example 4, where we found a maximum at x equals 0 and a minimum at x equals negative 1/6. And the question again is, are either of these local extrema also absolute extrema, an absolute maximum or minimum? We'll again consider the end behavior by taking the limit as x approaches positive and negative infinity. We consider the term with the highest power, which in this case would be negative 4x cubed. So we'll take negative 4 times some large positive value squared. That large positive number times negative 4 will end up being negative. So that end behavior will be negative infinity. And the limit as x approaches negative infinity of negative 4x cubed will be negative 4 times some very, very, very small negative number cubed. A negative number cubed will stay negative, so we get a negative times a negative, which yields positive infinity. Since our function is headed to negative infinity on one end and positive infinity on the other end, it doesn't matter what's happening in between. Any extrema that we identified are just local extrema. So no absolute extrema exist. In order for an absolute maximum or minimum to occur, the end behavior needs to be the same in both directions, or maybe approaching a horizontal asymptote. But if it's headed off to positive infinity in one direction, negative infinity in another, we know no absolute extrema can exist.